Right. We start with Gauss law. Gauss law doesn't have any proof, but it can be explained for one generic case of the sphere, which we did yesterday, we'll do today also. So let's write Gauss law. The net electric flux, the net electric flux through a closed means 3D, right? Mark the words closed, mark the words 3D. The net electric flux through a closed surface 3D is 1 by epsilon naught times the net charge enclosed inside it. Point to be noted here are closed 3D surface, net charge, and another point is the net electric flux, right? Net means if you have more than one, the condition of net will come in, and it is for 3D surface. Okay, Gauss law is not applicable for 2D surfaces. Children, whatever I write in this chapter, in this section of the chapter here, they're very important. You have to be very careful with these things. It is not applicable for 2D surface, right? It is only applicable for 3D closed surfaces, and the net electric flux is given by the net charge that is enclosed inside it. Okay, at this junction, what we will do, we will once again recall electric flux, okay, whatever we had studied. So at this junction, we recall electric flux so that our understanding becomes absolutely clear. Recall electric flux, a quantity which is denoted by phi E. So number one, you studied phi of E is equal to the dot product of E dot A. You studied this, right? That means this is a scalar, so it will be EA cos theta, where theta is the angle between them, right? Okay, then we also studied that if you take small electric flux d phi E, then it is E and then it is dot dA, and this becomes EdA, again cos of theta. The third one, you studied that electric flux is also given as closed surface integral E dot dA. The difference, this is when you apply electric field is uniform, electric field uniform. If the electric field is non-uniform, at that time we integrate. Like if you remember in grade 11, work is force into displacement, but we also do work equal to integral F dot ds. That is when the force is not uniform. So in this case, when E is not uniform, so this is a mother what you call statement which will always hold true, right? We further write that Gauss law has no proof. You do not prove Gauss law, but you can prove hypothetical scenarios in it. So based on this statement, we say the net flux of a closed surface, and this closed surface is what, beta? A 3D surface is given by epsilon naught, and this is given by Q net inside, and this is also given as integral E dot dA, or in some books you will find it is written as ds, whatever it is, E dot dA, and this is known as the closed surface integral. Note down these things. Q net inside. Some further points. Further points. One, shape and size. Shape and size of the closed surface does not matter. Why it does not matter? Because you see the formula. The formula does not have any sort of thing which is dependent on the shape and size. Does not matter. Okay? Phi E depends only on net charge inside the 3D surface. So children, do you recall in our last class we did for a cuboid, then we did for a cylinder, which were all empty. There was no charge, and you had got what is the electric flux? 0, right? So it only depends on the net charge. So this definition says if Q is only charge inside a 3D surface, then phi net will be equal to Q by epsilon naught. This is what we are trying to say. If Q is the only charge, any doubt at this position? Phi E is E dot dA. We use this formula beta when the electric field is not uniform. Is it clear now? Okay. So what we do, we see yesterday's scenario once again. We will see a sphere. So let's pick up a sphere which is enclosing a charge Q inside it. So let's have a sphere, and this sphere encloses a, we have a 3D sphere, and this 3D sphere encloses a charge Q inside it. There's nothing to do with whether the charge is this Q inside it, right at the center. So we write a closed surface. And what is your closed surface? A sphere of radius equal to R encloses a charge Q at its center. Right. Now the sphere itself becomes a Gaussian surface. Next we will talk about what a Gaussian surface is. Now you can so what happens, children? What is the use of this formula? There will be many scenarios where there will be charges which are scattered and you have to calculate the electric flux. The best way is to put one Gaussian surface. Gaussian surface means something. It can be a sphere, it can be a cylinder, like your school dustbin, the steel dustbins, or the waste paper basket with the top chopped off and the bottom chopped off, and you're just going to place it in such a manner that the Q can be symmetrically at the center of such object. Now this is a 3D sphere, so the 3D sphere has got a charge right at the center. That means the charge is at an equal distance from the surface from all points. And what is that distance? The radius of this, right? Enclosed surface at its center. So by Gauss law we can say that the phi due to this charge will be equal to Q divided by epsilon naught. This is what the Gauss law tells us. So let us see whether this actually is true or not. So what do we take? We take a small surface out here and we call this surface as dA. I have taken a small infinitesimal surface dA on the surface. Now children, go by your logic and tell me what should be the area vector from dA. The area vector should be coming out of dA, which is normal to the surface. From a football, we have got a football. In that football, we have got those pentagonal leather patches. Have you seen in a football we have patch? There one patch is dA. From that patch, what is coming out? Area vector is coming out normally. So this is dA, and this is my dA area vector. Now ask yourself another question, that this being a positive charge, this is plus q, this is a positive charge plus q, encloses a positive charge plus q at the center. So plus q is going to have its electric fields which will be radiated all radially outwards, just like the coronavirus like spoke. So for this point also there will be an electric vector which will come out, and that electric vector would be such, field vector would be such that it will come out in the same line. So there will be an E out here also. Agreed? So what do? We consider a small area element dA such that area vector dA is normal to dA surface. Area vector dA is normal to area surface. E is electric field due to Q and is radially outwards from center. So E vector and dA vector have an angle theta equal to 0 degree between them. Did you understand this logic? 0 degree between them. Fine. Now flux, small flux d phi e, this is d phi e, is flux due to element dA and E. So d phi e can be written as EdA cos of 0, which is EdA. Fine. We write net flux from the sphere is equal to phi e, and phi e will be integrating closed surface all small d phi e's. Phi e is integrating all closed d phi e's. So what do? We get phi e as integral E dA, right? E being uniform can be taken out of the integral phi dA. The value of E, so phi E, the value of E is how much? What is E? You're measuring E where? You're measuring E at a point where? At a point on the center. So this is this. So at a point here. So this distance is how much? This distance is R. So if you want to measure, measure the electric field at this point, the distance would still be R. So electric field is given by KQ by R square. And this is the total surface area of a sphere, which is 4 pi R square. R square takes off R square. Right? So phi E is given as 1 by 4 pi epsilon naught. Okay. It should be more specific also. The sphere has only air inside it. Multiplied by Q, multiplied by 4 pi. The 4 pi takes away, so it becomes Q by epsilon naught. Perfecto? Can I change? Okay. Yeah, take your time. Understand and write it. We also said that the shape does not matter. It only matters what you have taken inside it, or what is the charge inside it. This is a surface integral of a patch dA of a sphere. If you integrate all the dAs of a sphere, what do you get? The sphere. We'll just debate this point where we said point number 2, shape and size of the closed surface does not matter. Are we done? Can I change, Neha? Okay, shape and size does not matter. And what I mean by shape and size is, give me the option to draw 3D and here 3D. Geometry, shapes. Okay, we don't have. So say suppose I have a cylinder. The next shape is I have a cuboid. And say the next shape is I have a cone. Let's say I have a cone, right? I've got three 3D shapes and I have a charge. I have a charge right at the center, which is Q. I have a charge right at the center, which is Q. I have a charge right at the center, Q, right? So here what will not matter is the flux in this case, phi E, will be Q by epsilon naught, as long as it is in free space. Here also the flux will be Q by epsilon naught, and here also the flux will be phi will be equal to Q by epsilon naught. This is for your understanding. It does not change on what type of shape you are considering. It will only change on whether the net charge inside it is getting changed or not. Okay, so Q should be inside. Okay, and the closed surface, such closed surfaces can be also considered as a Gaussian surface. Now we will see about Gaussian surface. Here it may not be a Gaussian surface. A Gaussian surface should be symmetric about the charge. So how do you make it a Gaussian surface? You can make a cylinder on this side and you can make a cylinder on this side. So it becomes a big cylinder which is equal to the 2 times the height of the cone, such that the charge is at a symmetric center of it. That is what is the idea all about. Do you get it? Suppose you have got a disc. You have got a disc, DVD disc, and the charge is at the center. Now this is a 2D. Gauss law is only applicable for 3D. So you can have one cylinder on this side. You can have one cylinder on this side. Now it's a big tube on whose center that charge is lying. This is the idea that we will be employing. Okay. Now Q is the net charge inside Gaussian surface and not outside. Okay. Now when you calculate, now this is important. So our formula says that the flux is given by Q inside, remember it, Q inside divided by epsilon naught. So you have to have something which is known as the Gaussian surface. And how to choose the Gaussian surface? Gaussian surface means it will be a 3D surface, closed surface. Gaussian surface, and Q inside the Gaussian surface matters. Surface only contributes to phi E. So let's understand one hypothetical scenario. That hypothetical scenario is like this. Let's see this. Right. I have a charge Q which is inside called Q1, and I have a charge Q2 out here. So this is interesting. Okay. I have one Q1 and I have one Q2. Okay. Okay. Now, here we'll say Q1 contributes to phi E. Q2 does not contribute. Remember this very, very nice. Q2 has no role on the flux. However, when you write the flux as phi E is equal to closed surface integral E dot dA, remember this? Q2 contributes to this E, Q1 also contributes to the E, because the electric field is also the net electric field. So the electric field will be contributed by both the charges, but the flux calculation will be, means when you are doing this part, if you are suppose doing this part, then both matter. But if you are trying to calculate this, then only the charge inside matters. The charge outside does not matter. Okay. We'll talk more about Gaussian surface. As of now, just understand a Gaussian surface could be the 3D object itself. Now, question arises, sir, do we choose a Gaussian surface every time? Well, not. If the 3D object is such that the charge is right at the symmetric center of that 3D object, then the 3D object itself is the Gaussian surface. For example, here I will not choose another Gaussian surface. This itself is the Gaussian surface. But for that cone, that is not the Gaussian surface. The charge is not at the center of it. Right? Okay. Our next point says that the dA, like suppose, for example, say suppose you have a surface like this. You have a surface like this, and there is a charge Q which is out here. There's a charge which is out here, right? So let's have a look at the electric field lines. Okay. Now, are you able to understand? This is a small patch of a Gaussian surface, small patch of a Gaussian surface. It can be from a cylinder, it can be from a sphere, it can be from a cuboid. So what do we say is, suppose this surface does not enclose any charge. Let's say this surface is not enclosing any charge. Then what happens? Okay. Now from this Q, don't you think there will be electric field lines which will be radially coming outside all directions? I am only worried on how many field lines are coming in my, how many field lines are coming through my particular patch. Right? Let's say so much of field lines are coming out. There will be field lines here also. But this surface does not have any charge inside. Right? This you have done already. You have proved it. Don't you think that if there is an electric field, then let us consider a small patch out here. Small patch out here. There's a charge, there's a surface. The charge is here, the surface is here, the charge is here. The electric field line is going out like this. There will be electric field line coming out like this also. For this, there's a small area element here. Whichever area we are puncturing, there's an area element. For each of these area element, if this is a 2D surface, if this is a 2D surface, don't you think there will be area vector on the, but in 2D we have got two area vectors. In 2Ds we have two area vectors. Suppose it's a 2D sheet. This is a sheet, and this is a sheet, and the charge is here, somewhere here. So how the area vectors are coming out? How are the flux coming out? So the flux are coming out. So the charge is here. This way the flux are coming. The electric fields are coming out in this manner, right? Here there is a small area element. Agreed? For this there will be a normal on this side. For this also there will be a normal on this side. There will be a normal on the reverse sides also, because it's a 2D surface now. So what I'm trying to say is that there will be an area vector which will be coming out in this side. There will be a dA. There will also be an area vector on this side, right? Similarly, wherever it punctures, there will be 2dA. Well, what will be the flux for associated with this? EdA cos 0, EdA cos 180. So they cancel each other. because there is no net charge inside. That's how you get it 0. Recall your that diagram. You had that cube. Top and bottom used to cancel each other 90 degree. Front and back used to be 90. The sides used to be EDA minus EDA. So they cancel each other. Right. Now, so this explanation you have understood. And you should also, so it depends upon the charge that is inside. And in this thing, we will add one more. Polarity of charge is to be considered. Is to be considered. This is very important. Means you have Q1 positive inside. If there was a negative Q1 inside, the flux would have been 0 because Q net would have been 0. Plus 5 coulomb and minus 2 coulomb. What is Q net? 3 coulomb. 3 by epsilon naught it will be. 3 by epsilon naught. Okay. 3 by epsilon naught. So we say it's the polarity has to be considered. And electric field, this I have said, net flux through the 3D surface, net charge inside, net electric field. The electric field will be net due to this. Similarly, okay, now one more question. General knowledge. Suppose I have a closed surface. And inside the closed surface, I have a dipole. What should be the flux? 0. The dipole is a system of two charges which are equal and opposite in their magnitude. So the net charge, dipole means what? A dipole has got a plus Q, a dipole has got a minus Q. So if you try to calculate what is Q net, you will say it is 0. And therefore your flux becomes 0 by epsilon naught, which is equal to 0. These are very important, okay? Number one, polarity of charge is to be considered. Q inside only contributes to flux. Q outside contributes to the net electric field. If you have a dipole, then the flux is equal to 0. These are important things. These are important things. And if the charge is not inside. So later on we will find, children, that we are using Gaussian surface to evaluate criterias. But say my surface, 3D surface is like a potato. The shape of a potato. It's a 3D surface. It has a charge Q inside. What is the flux? Q by epsilon naught. And my 3D surface is a Wagoner car which has got a charge inside. What is the flux? Q by epsilon naught. My 3D surface is an Airbus A320 with a charge inside. Q by epsilon naught. The shape does not matter to us. Okay. Now, when to apply Gauss law and when not to apply Gauss law. So some statements we will see and we will write. So you write, there's a very nice thing, very nice statement, and that statement says Gauss law is always applicable. It's a law, so it will always applicable, but not always helpful. What do you mean by the word helpful? Helpful means this law lets me calculate the net flux through a 3D surface. If you are not able to calculate the net flux, then the law is not helping you. But the law is applicable. Now, why is the law not helping you? The law says flux is equal to Q by epsilon naught. And what is the flux? Integral E dot dA. Epsilon naught is not your problem. You always know what is the value. 8.854, 10 to the power minus 12. Q, you will know what is inside. What is causing you problem is that integral E dot dA. You have to equate it, right? E dot dA. That means that integral is not solvable for you. So when is the integral not solvable for you? That in all those cases we will say it is applicable, but it is not helpful for me. So number one, let's write, when is it useful for you? Okay, the useful by now you have understood all the scenarios that you have seen so far. Okay, number one, Gaussian surface should be symmetric about the charge distribution. Now, why do you say this? See the formulas that you used. You took a sphere and you took the sphere in such a way that the charge was right at its center, and you started calculating dA, closed surface integral. You could calculate the dA giving the A for the sphere. So the 3D surface was uniform or symmetric about the charge distribution. If it was not a sphere or a cylinder, then also my dA would have been helpful, because it is symmetric about the distribution. If it was a cuboid also, it would have been helpful. If it was a cube also, it would have been helpful. But if it would have been a cone, it would have not been helpful. In that case, we have to design a Gaussian surface, right? You have to design. But if it was something like a potato or something, then it is not uniform, right? So the Gaussian surface should be symmetric about the charge distribution, number one. Number two, we say the electric field E, must be equal and same. Equal and same. So must be, we use the word symmetric. Okay, now you can say, sir, you said that if the electric field varies, even if it is varies, it should be symmetric. Symmetric at all points on the Gaussian surface. At all points means at all symmetric points. Suppose you are on this side of the sphere and you are on that side of the sphere, the electric field should be same. It is say XX. Understood? But you are at a point little bit, say y distance. If the electric field is T, on the other side at y distance also it should be T. This is called symmetric. Are you understanding? No. How to understand it? You have to understand it symmetric is the. How many floors are there in this tower? 19 floors. Let's say we have got 18 floors, just like titanium. At the 9th floor, you are at the middle. Stand at the 9th floor and take a tower right in front of you, which is another 18 floor tower, and make another person stand at that 9th floor, right? Now, as you look at person standing each floor up, your distances are symmetric. Means the 9th floor person hypotenuse and the 7th floor person hypotenuse are equal. Do you get it? The 10th floor person and the 6th floor person, it will be same. But that won't be same with the 7th floor and the 9th floor person. It's like this. You are looking here. These two will be same. These two will be same. But this and this won't be same. So at all points, it should be symmetric. If you are say X here, its symmetric point also you should be symmetric at all points. That's what it's trying to say. The electric field should be symmetric at all points on the Gaussian surface. Gaussian surface. And they'll give you a problem like this only. Else which we say else which Gauss law is valid. But mathematical computation is difficult. Mathematical computation is difficult. It's not that easy. Point number 3. This is important. This is you will use in your grade 12. Gaussian surface must not cross over or cover a charge. Something like this. let's say you have a Gaussian surface here, this is a cone, and you have a charge out here, this is not allowed. The Gaussian surface cannot cross over or cover any charge. Your idea is that the Gaussian surface should always enclose the charge. It should not cover all this thing. So a 3D surface and Gaussian surface may be two different surfaces, because Gaussian surface is hypothetical. So the question might come with a 3D surface. You might assume another Gaussian surface. A 3D surface may be different from a Gaussian surface. Okay, children, look at this example which I gave you. Look at this example which I gave you. The scenario is such that this is a birthday cap which has a charge right at the apex. Possible? Possible. Now we have to calculate the flux due to this charge. For this problem, you cannot take the cone as the Gaussian surface. What we will do, we will have a hypothetical Gaussian surface which will be something like a cylinder where the charge is now at the center. Understood? And now we will calculate E dot dA. You will be able to calculate E dot dA. You will get the value of the whole cylinder's curved surface area, right? Because these will be the ones who will be responsible. Just these two surfaces will be responsible, right? Because here the charges will be the electric field on this side and the charge on this side. The electric field on this side and the charge on this side will be negative. So these two will eliminate each other, and only the one due to the curved surface area will be helping you. So now if you dot E dot dA, you will get 2 pi RH. Are you understanding what I'm saying? And then you can calculate that pi RH into that electric field should be equal to Q by epsilon naught. So we say so let's understand one thing very nicely. Children, if they ask us to calculate the flux due to a charge and they give us a figure, the figure can be of 3 different types. The figure can have the charge right symmetric within it, and the figure itself is also symmetric. That itself becomes my Gaussian surface. The figure can have the charge on one edge of it, but the figure is symmetric. I have to think of a Gaussian surface so that the charge can now be at the center of the Gaussian surface. Another is the figure covers the charge, then also you have to build a hypothetical Gaussian surface. Are we clear on these 3 things? Can we now take up some problems and some examples? So all we do, what children? We will be doing. So you will say, sir, the flux should be Q by epsilon naught. Q by epsilon naught it is when it is a Gaussian surface. This is what the books miss a bit, I think, at our level, or children get confused. I also used to think Gauss law says Q by epsilon naught, then what is the fun? You just write Q by, no. Q by epsilon naught is absolutely valid. The formula is valid. But Q by epsilon naught comes when your Gaussian surface is like this. Q by epsilon naught when the Q is inside a Gaussian surface. In this case, my 3D surface and Gaussian surface is same. Formula is valid. I can just write Q by epsilon naught. In this case, my given surface, which I will always call as what? 3D surface, closed surface, and Gaussian surface is same. Here also answer will be Q by epsilon naught. Here also answer will be Q by. Here it will be, but we will see whether it is or not. Understood? So let's take some scenarios and see what happens in our charge distribution flux calculation. So let's take our first example, and our first example is somewhat like this. Okay, so my first example is I have a charge. 1 minute, children. This is my first question, and the charge is seen. The charge is seen right at the center of the top surface. Find. So we write our question as Find electric flux. Find electric flux through the semi-cylinder. Find electric flux through the semi-cylinder. Now ask yourself the question. Can the given 3D surface be taken as your Gaussian surface? Well, no, you can't take this as your Gaussian surface. So what will you do in this case? You have to build one Gaussian surface, okay? And the Gaussian surface would be in such a manner that my Gaussian surface would be, now let's say this is here, I clone it. Now this is my Gaussian surface. My solution. So the Gaussian surface is taken in such a way. Let's see our Gaussian surface. Gaussian surface is a cylinder of length, right? They told you that this is a semi-cylinder. So let's say this semi-cylinder was given to you with a length of L by 2 and a radius of R. So Gaussian surface is a cylinder of length L. Gaussian surface becomes a cylinder which is L. Okay. So this much is L by 2 and this much is also L by 2. L by 2, L by 2. Now you tell the flux phi E through the Gaussian surface is equal to how much? Q by epsilon naught. Phi E through half the Gaussian surface. Now children, you can understand the symmetry pattern. Are you getting it, what we are trying to address here? Through the flux will be always symmetric. Gaussian surface is such assumed that the flux is always symmetric throughout the Gaussian surface. Remember, charge will be, I will assume a Gaussian surface which is symmetric for the charge to be at its center, number one. In that case, the Gaussian surface will allow me to calculate the flux as per Gauss law. Once I have calculated the flux for the Gaussian surface, the flux is always uniform symmetrically throughout the Gaussian surface. So for the whole Gaussian surface, if the flux is say x, for 3/4 of the Gaussian surface, the flux will be 3/4 of x. It is like that. Are you understanding? Right. So it is symmetric. Now, through half the Gaussian surface is equal to, what is half the Gaussian surface? Half the Gaussian surface is my, why am I right? Is equal to my 3D surface, or I call it as my closed surface, or this is nothing but my semi-cylinder, will be equal to half of Q by epsilon naught, which is equal to Q by Q epsilon naught. This addresses the symmetry portion. Children, did you understand? For the Gaussian surface, it will be Q by epsilon naught. So for half the Gaussian surface, it is half Q by epsilon naught. What is half the Gaussian surface? The original 3D surface of the question, which I call as my object, or in this question, the object is, it was specified that the object is a semi-cylinder. Did you understand how we are doing it? Your object is a semi-cylinder. What is the 3D object? Semi-cylinder. And how much proportion is it of the Gaussian surface? Half. Surface means it is actually 3D. It is half. Proportion is half. So how much will it contribute? Okay, now you try to evaluate. Question will be very simple. Okay, shall we? You try to evaluate. You need to evaluate now. Question: evaluate flux. Do you want me to change to the previous screen? Evaluate flux phi e through given closed surface, given closed surface or 3D surface. Now, what is the given closed surface to you? The given closed surface, children, is a hemispherical ball. Okay, the given closed surface is a hemispherical ball. Fine. And my charge is located here. Can I take my 3D object as the Gaussian surface? No. So what will be my ideal Gaussian surface? My ideal Gaussian surface would be a sphere of the same radius. Would be a sphere of the same radius. My ideal Gaussian surface would be a sphere of the same radius. Now what do I write? I would write phi e through the Gaussian surface. You have to first write what is the Gaussian surface you have selected. So let's write that. What is our Gaussian surface? Our Gaussian surface is a sphere of radius equal to given hemisphere. Now phi through the Gaussian surface will be equal to how much, children? Q by epsilon naught. Now, given 3D surface is how much proportion of the Gaussian surface? Half. Half of the Gaussian surface. So phi through half Gaussian surface is equal to phi through given 3D surface, and this should be equal to how much? Q by 2 epsilon naught. See, it's so easy. Next one is interesting. Shall we change? Okay, let's see the next one. This is a square sheet. This is, children, a square sheet. This is a square sheet whose sides are AAA. This is a square sheet whose sides are AAA. Agreed? All right. And let me etch this so that you understand it properly. And the charge is here called Q, which is at a distance half A from here. Half A from here. Right? Clear? Let us try to imagine the Gaussian surface. Actually, very easy. You need not like break your head for this. Okay, this is easy. So let's say, imagine that my Gaussian surface is a cube. My Gaussian surface is a cube. Is this understood? You had a sheet. Let me name my sheet as let me name the sheet as PQRS. Charge is where half A above the sheet. Can I not make this as PQRS, children? And this is my sheet. Where is the charge? Half from here. So the charge is right at the center now. Do you agree? Right at the center. And if you go this side, it is half. So A. Right. So my Gaussian surface for this problem, the Gaussian surface is a cube of edge which is equal to A. Gaussian surface is a cube of edge A, and the charge is right at the center. At center. So the flux through the Gaussian surface will be how much equal to, children? Q by epsilon naught. What is your 3D object or object? It's a sheet. It's a sheet, right? And this sheet is what part of your Gaussian surface? One face of the Gaussian surface. How much are you of the Gaussian surface? 1/6 of the Gaussian surface. The Gaussian surface has got how many? 6 sides. All symmetric and equal. And you are one side of it. So if I say that flux through the, it's in question if we say flux through the plate. Now my plate is equal to 1/6 of the Gaussian surface is equal to flux through 1/6 of Gaussian surface, which is Q by 6 epsilon. Let's change this problem a bit, okay? Let's change this problem and let us ask the question in this manner. Could you understand what how we calculated the previous one? Let's change this question. And I now have a cube like this. The question itself says, now the 3D surface, now given 3D surface, I uploaded some books and all, right? Given that the 3D surface is a cube, Q is at center. Q is at center. No questions asked, right? And I tell you, find the flux through the face ABCD. Try to find out the flux through the face ABCD. You try to find out what is it. Now, can I consider my cube as the Gaussian surface? Yes. The 3D object itself is the Gaussian surface. How much is the flux? Q by epsilon naught. Q by epsilon naught. But I am asked to find out the flux through ABCD. How much is ABCD of the Gaussian surface? 1/6. So what is the flux? 6. Right? So here I can say this 3D surface itself is the Gaussian surface. So phi through the Gaussian surface is same as phi through the 3D surface. And this is equal to Q by epsilon naught. My plate ABCD is 1 by 6 into 3D surface is 1 by and is equal to 1 by 6 Gaussian surface. Therefore, the flux E through ABCD will become how much? Q by 6 epsilon naught. We have nothing more to do in this chapter. All done. And now what we are left with is you should do like problems. Can you take one problem and try to do this at home? Okay, one problem I'm giving you, and your problem is like this. Say your question is, the given 3D surface is a cube. Given 3D surface is a cube and charges is here, or say the charge is here. This is Q. What is the flux through the given 3D surface? What will you do, children? What will you do in this case? Attach one more cube. Attach one more cube. Attach one more cube. Attach 4 more on that sides. You will make, have you studied the solids have been taken away from chemistry from you? This is like a body-centered cube. Have you seen your Rubik cube? Mark any one corner of it as the charge. How many cubes will you need to build one such a cube where this will come at center? I think 8 cubes. 1, 2, 3, 4. See, this is the cube on which it is at the edge. 1 cube, 2 cube, 3 cube, 4 cube. Now you have made half of a cuboid. Bring 4 more cubes on that side. This will go at the center. I think its answer will be Q by 8 epsilon naught. 1/8 of the whole cube. 8 such cubes will make 1 cube. So for your understanding purpose, we can do it like this. See, just see one diagram. It will become interesting. Okay, let's just make 1 cube, small in size. Have you understood this? Fine. Where is your charge, children? Charge I will draw later. Mark this cube. We'll draw the charge later. Charge is somewhere here. Okay. So let's build this. Let's build. Yeah. Clone. The first cube will come here. Some gaps I'm leaving so that it becomes easy for you. Then, 1 minute. Okay. Then 1 more here. Some gaps. Then 1 more here. Can you still identify where your charge was? Your charge was here, right? Okay, clone. 1 more right at this place. Fine. Clone this. 1 more. One more right at the back. This will become complicated now. Yeah, 1 more like this. And now 2 more. 1 more here. And 1 more. Yeah. Yep. We're almost done. And if you remember, our charge was here. This is called a body-centered cube. 8. Fine. 8 times I cloned it. So your 3D surface is how much of the Gaussian surface? 1/8. So the flux becomes 1/8, Q by 8. That's it. Let's take one class more on some numericals if possible, and then we move to our next chapter of the last chapter of electrostatics, which will be electric potential and capacitance. Okay.